All right, welcome back. So now that we've taken a look at some of the network virtualization overhead and a particular feature that the VMXNet 3 adapter offers by offering full memory reservation in your VM with memory being pre-allocated and pinned, thereby making the network adapter more optimized, another characteristic you have on VMXNet 3 is actually on the CPU side of things. Did we know, or did you know, that when you have a VM with more than one virtual NIC, that may not be something that happens very often, but if a VM has more than one virtual NIC, and you might have done that to increase the potential throughput in and out of the VM's network capabilities, right? You would assume if you give a VM 2 virtual network adapters, that would have improved the throughput to that guess, and it does. However, it can make it even higher levels of throughput if you gave the VM extra CPU networking threads for these network adapters. By default, even though you gave a VM 2 virtual NICs, likely, well, if you gave the VM 2 virtual NICs, there's actually only one networking thread to handle those 2 virtual NICs. So that basically means one CPU thread on your hardware will be utilized to handle the 2 threads. And that may not be a big deal that there is only one CPU networking thread, but what you can do is you can actually dedicate a different CPU thread for each of the different virtual NICs in the VM. So for those VMs that need the high network throughput and you gave them 2 network adapters in order to take advantage of this, well, you just want to make sure if you needed to test this out, this is the parameter to verify. There's 2 settings that you'd have to apply in your VMX file. Basically, for each of the network adapters, they would need to be set with this parameter called Ethernet 0 or Ethernet 1, depending on which network adapter we're applying it to. And then this parameter called CTX per dev. It means contexts per device. The normal is 2. So if you ever look at a VMX file, these parameters aren't there because they default to 2. This is just stating this is what the default is. The parameter is set to 2, which basically means there's a single transmit thread for the entire VM, regardless of how many network adapters the VM has. If, on the other hand, here I have my 2 adapters, I want to have a dedicated transmit thread for each of the different virtual NICs. Setting this parameter to 1 will guarantee it. You're simply saying one dedicated thread, right? One dedicated transmit thread for each of these adapters. 2 doesn't mean they're guaranteed to 2. What it means is that it's the whole VM. So 2 means the whole VM. 1 means one transmit thread per virtual NIC. But wait, there's more. If there are a high number of TCP-related network activities that you'd want to make sure there is an increased amount of TCP throughput, maybe increase your TCP buffer inside your guest operating systems. But if there are multiple TCP threads that you'd want to have more efficient streaming, another option is to set this parameter, the same parameter, to 3. And what that does, it lets the actual system determine how many transmit threads based on the TCP transmissions that are going on and out with that particular virtual machine. So it's not a value of 3, or I should say, this does not mean there are 3 threads. What it means is that the system will auto adjust for anywhere between 2 to 8 threads per virtual NIC. So this would potentially improve your overall networking throughput in terms of outbound TCP traffic. So this is an interesting adjustment that you can make on a per VM basis, or you can actually make the same adjustment for an entire ESXi host. That would apply to all virtual machines. There's a parameter as an advanced system setting called net.net.tx.ty type. And this has the same exact parameters. There's 1, 2, or 3. If you set it to 2, which is the default, it's 1 thread per VM for every single VM on the system. Set it to 1 will make it guaranteed that there'll be 1 thread for every virtual NIC that you have on your server. So any VMs that have 2 NICs will get 1 thread per virtual NIC in the VMs. And if you set it to 3, each VM will auto adjust between 2 to 8 per virtual NIC. So that's interesting. If you set this to 3 here, or if you set it to 3 on an individual virtual machine, it really doesn't matter if the VM has 1, 2, or however many network adapters. It's going to auto adjust the threads per adapter. So if the VM only has just 1 adapter, it will still adjust it so that they're between 2 to 8 threads because of heavy TCP traffic. So it's an interesting setting. If I were to set it to 3 here, it would auto adjust for any VM that's on that host. Keep in mind, this is quite different, but has some similarities to that VMXNet3 optimization that we covered just before in the previous lesson or previous section, where there was essentially dedicating memory to improve networking throughput. Here, we're actually dedicating CPU resources to improve networking TCP throughput. But it's something to consider, not to say you should, right? This is why some of these parameters are not the default settings. These may or may not be a positive thing for every single situation. You'd want to test these out, but be aware they are here and they're available for those network intensive types of applications that you would be virtualizing. Now, some are more standard, like for instance, TCP segmentation offloading. This is a great feature. It's been in the product for years and years, and it's basically part of the VMXNet 3 and even the VMXNet 2 capabilities, right? This is where if your networking hardware has this feature, which most do, this is a design or a feature that's quite mature nowadays, where that one of the important functions of the Ethernet layer is to ensure we have a proper frame size. And so the IP layer will make sure the packet being passed down to Ethernet layer is of the same appropriate frame size. But even, of course, the TCP layer is going to do that, since the TCP is formulating its packet based on your frame size. So if it's being handled by the TCP layer inside the guest OS, that means that there is virtual CPU time responsible for segmenting the stream of data that you're needing to transmit based on the size of the Ethernet frame. If this could be handed off to the network adapter, this is one less thing that the virtual CPU has to be responsible for in the guest OS. So again, this is something that's in almost every adapter these days. It does need to be enabled in some cases. So TCP segmentation offloading is a really powerful thing. You just need to have VMXNet 3 or VMXNet 2. It's been in that one as well. But basically, anybody who has the VMXNet 3 adapter, they get this capability. Just verify it's enabled in the device driver in your guest OS. By the way, this is also something that is available for VM kernel ports too. So this is actually quite significant for things like vMotion traffic, being able to transmit large amounts of memory for vMotion purposes, and having the TCP layer inside the VM kernel to let the network adapter handle the TCP segmentation functionality has improved even vMotion throughput, or even software-initiated iSCSI throughput, again, going through the VM kernel to gain access to the network. So these are things that can be enabled in the VM kernel for devices that support TCP segmentation offloading. It can also be enabled in the guest. The good news is that it already is enabled in the VM kernel, so there's nothing we need to do in the VM kernel to make this happen. What this is referring to is something that in the guest. If you got the VMXNet 3, you've got this feature. You just need to make sure that the actual setting in the guest, TCP segmentation offloading, is enabled. And that may vary from guest to guest. So something to just verify. But it can be quite a significant offloading capability. Jumbo frames also another great offloading capability, where if you've got the higher network capabilities from 10 gigabits and greater, the overhead of handling that many more Ethernet frames at 1500 bytes can be quite a CPU overhead producer in itself. So increasing your frame size to 9000 bytes reduces the number of frames to manage, reduces the CPU overhead for managing all the extra Ethernet frames. The only thing about jumbo frames, it needs to be set everywhere, right? On the physical switches that we're connected to the virtual switches inside the ESX servers, onto the VM kernel ports, into the guest OSs. It has to be set end to end. And anywhere where it's not, it'll need to be resent with a refragmentation requirement. So that's the caveat with jumbo frames, but it can be very powerful, of course, with these faster speed networks that we have today. And let's see here, what else we have here? The VMXNet 3 supports split RX mode. This was introduced in vSphere 6.5. This is, in fact, an ability for when an ESX server sees that there are literally thousands of incoming broadcast packets or thousands of multicast packets. Normally, of course, a broadcast or multicast packet is one packet that arrives. Because it's in a broadcast state, it hits either in broadcast every single node on the network, or in the case of multicast, it's going to only those nodes that are a member of the multicast group. But still, as it arrives in an ESX server as a single packet, the ESX server now has to then disseminate this single packet to all the VMs that are being broadcasted to, or all the VMs that are being multicasted to. If we're dealing with a situation of 10,000 broadcast packets per second, and the system is basically handling this with a single threaded function, this can actually put a bit of a burden on the system. So the system automatically discovers when this situation is occurring and will actually become multi-threaded in how it disseminates this single incoming broadcast packet to all the VMs that need it on that host, so that it doesn't have to be dedicated to just one thread and causing a potential bottleneck. But it's an automatic feature. You don't need to enable this, so it's a pretty cool thing to have. I can imagine, though, if we're sending 10,000 broadcast packets per second, that's a pretty intensive broadcast operation for sure. Now, another parameter called split TX, which is not the opposite of split RX. I mean, they are different interactions, right? Split RX is inbound. Split TX is outbound, right? So split RX deals with incoming thousands and thousands of broadcast packets. Well, split TX is basically the process of a VM transmitting traffic out to the physical network. I'm sure they do this from time to time. And so this is from virtual NIC to virtual switch, and then again from virtual switch to physical NIC. The processing can be parallelized with split TX mode, improving the throughput by having a further level of concurrent capabilities here, increasing that parallelization between VM to virtual switch and then virtual switch to physical NIC. This one actually is disabled by default though. So if you wanted to enable it, you have to see what the benefits is. It may bump up your CPU usage for this one as well. You actually have to run this command called Visish, which is not a command a lot of customers end up using kind of on their own. They're usually on the phone with our global support to kind of direct us to using this command. This command can do lots of things, but this command in this example is actually setting TX mode to 1, right? So just keep in mind the syntax of this command, you'll need to provide, you're assigning it to the actual physical adapter that we're passing this traffic through. So you had to provide the VM NIC identifier here, and then you're setting this split TX mode to 1 to enable it. And then this improves your speeds at which the traffic passes through the kernel layers quite significantly. So taking a look at all of these things, right? How many of these were a case where these features were reducing the CPU overhead used for networking packet processing? Some of the things we talk about reduce CPU overhead. Some of these might actually increase the CPU overhead, but improve networking throughput as the benefit here. But we're talking about which one of these will actually reduce your CPU overhead. Well, taking a look at these, there's split TX mode. Would that reduce the CPU overhead? Well, that's actually bumping up the multi-threaded nature of it, so probably not. How about split RX mode? That's going to bump up CPU as well. Jumbo frames, though, that reduces CPU overhead. TCP segmentation offloading, that offloads onto the hardware, so that's going to reduce CPU overhead. And then having multiple CPU threads per virtual NIC, that's going to bump up your CPU there too. So really it is just number 3 and 4 here that are the CPU overhead reducer features. So this was a quick look at our networking performance factors. We described network virtualization overhead, described the network adapter features that affect performance, as well as vSphere networking features that affect performance. We'll take a quick break. We'll come back, and in our next lesson, we'll look at CPU performance monitoring metrics. So we'll take a break, and we'll see you in a few minutes.